Okay, so let me just briefly repeat that. So cons adds an element to the head of the list. Append concatenates two lists. If you use cons instead of append, then you will get a list where you have list as the first element. And append, yeah, I think so. Yeah, append should be linear in time, but that again depends on how exactly you interpret or compile this thing. We're talking about interpretation in Dr. Racket. Yes, this is linear. This is not very efficient, but of course you can apply some optimizations to make this fast, but it does not matter for us right now. So if you use append instead of cons, it will throw a runtime error because append expects a list, and if you give it a number, of course, there will be a problem. Okay, so another clarification is about tail call, tail recursion. So again, if you have a function that has a recursive call, now if you look here at these two definitions of factorial, in the first definition, whenever you compute factorial of some number n, you either get to 1, which is just the immediate result, or you get to an expression n times factorial of n minus 1, which contains the recursive call, but the recursive call is not like the outermost part of this expression. It's somewhere inside. Now, this is a recursive call, but it's not a tail call. On the other hand, we can sort of refactor our factorial using a helper function, which, as I explained before, introduces an extra parameter which keeps track of the current state. So we are multiplying, but we are keeping track of the current product. So in this case, if we compute helper with some values of current and n, we either will get an expression current, which will just return the result, or we will get an expression helper of, and then two arguments, n times current and n minus 1. But here in the second expression, helper is the outermost function call. So the entire expression that we get is the recursive call. And this is what we refer to as the tail call. Now, having a tail call is important, as I've shown in the previous lecture, to keep the expression small while we're evaluating it, okay, as in particular in call by value. There's also something called tail call optimization. Maybe you have heard of this in compiler course, maybe not. Maybe some of you didn't have a compiler course yet. Yeah. Some of you didn't have it yet. So there is something called tail call optimization, where the idea is that this tail recursive call, instead of growing call stack, you just replace the last function call on the stack with this tail call. So that way, again, your call stack does not grow. So you do not get a stack overflow when you have these recursive, a lot of these recursive calls. Okay, very good. So today, we're going to talk a little bit about pairs and lists in Racket. We're going to mention quotation. And then the main course for today is higher order functions. We have seen a little bit of them before, but haven't really used them. And then maybe if we have time, we'll also talk about generators. Okay. So previously, we have used this cons to add an element to the beginning of the list, right? Now, cons, as I mentioned before, stands for constructor. It constructs a list out of its head and tail. Now, in Lisp-like languages, cons is not just able to construct lists, it actually constructs arbitrary pairs. So when we say cons 1 and 2, what we're doing is we're constructing a pair. If you run this in your interpreter, what you will see is this 1.2. Now, the dot is the Lisp notation for pairs. I think you cannot actually write dot in Racket. It's only how it displays it for some reason. But anyway, so you can just use any two values and you can build a pair out of them. So cons builds a pair. And so we had this predicate called cons with a question mark. Now, whenever we would like to talk about pairs, we will instead use a pair with a question mark. So what about lists then? Well, a list is in fact either empty or it's a pair of its head and the tail of the list, which is again, just some list. So when you do cons one empty, you're constructing a pair of one and an empty list. And that is exactly what a list in Racket is. It's just a pair. Well, it's either empty or it's a pair of a value and some other list. So lists are just a special case of pairs. Okay, does this make sense? Very good. Now, you can, of course, do things like cons 1 and then cons 2, 3, which means that you add 1 is your first element, and then you have a pair of 2 and 3, right? But now, if you do this in the interpreter, you will get this 1 space 2 dot 3. So what it means is that you indeed have a pair where the first element is 1 and the second element is the rest of whatever you have in the parentheses, which is 2.3. Okay. So in other words, you could write this also as 1 dot and then in the parentheses 2.3, but that would be too many symbols, I guess. So this is how you would find it written in the interpreter. Okay. So this is just a syntactic thing that you should probably be aware of because you might see it in the interpreter. Okay. Very good. Now, remember that to extract components of lists, we had these functions. First, there's also second, third, etc. And there is rest. So first, second, third extracts corresponding components of the list. So first returns the first, second returns the second, third, the third, etc. If there is any, right? And rest returns, well, the list containing all of the elements except for the first one. Now we would like to use the same things for the pair, but we cannot really use rest. Well, rest does not really make much sense for the pair to return like the second component, right? So there is a traditional, there are traditional functions, traditional names for functions that extract the first and the second components of pairs, which again, I mentioned last time. They're called car and CDR, which I think is pronounced CUDR. But yeah, they're not at all mnemonic, unless maybe Nikolai knows why they're called this way. I haven't been able. Yeah, so they're not mnemonic anyway. So yeah, so car is traditionally used to extract the first component of a pair and CUDR to extract the second component of a pair. Now, car is exactly the same as first. I mean, you can use them interchangeably. It's just that we're going to use first and rest when we're referring to lists, when we expect that the argument is the list, and we will use car and CUDR if we expect, if we were working with a pair. Okay. So that's just for us to understand better what we're dealing with. Yep. There are also weird combinations of these A's and D's in the middle that you can put there to refer to second, third, or even more weirder things. But you can just ignore that. That's not very helpful, I think. So now, we would like to be able to work with lists and lists of lists, and we would like to work with more weird structures like tree-like structures maybe, right? But if we would like to do that, it becomes very quickly very annoying to put a list or pair or cons everywhere in the source code. So I'm giving you this as a sort of convenience tool, but it can actually do more. This is a quotation operator. So what it does is it interprets its argument. It does not evaluate it. It just interprets this as exactly an S expression that we just returned. So what happens here is when we do this quote with a list of lists of 1, 2, 3, and 4, this is exactly what we get, right? So we're using this parenthesis, this exactly as lists, not as function calls, okay? So when we use it with quote. Now there's a short notation for quote, which is just putting a single quote before whatever expression you're dealing with. So here, and this is exactly what you see also in the output of the interpreter, okay? So this means whenever you put a quote, it means that whatever comes next is not evaluated and is just interpreted as a single value as is. Means there are no function calls, nothing is evaluated there. Yes, yes. So in fact, Lisps are very often used for metaprogramming and blah, blah, blah. We're not actually going into that. So that's why I'm not sort of going into much detail here. But if you're familiar with metaprogramming and macros, this is also for that. Okay, so you can use this to sort of simplify some constant expressions. For example, you can do the first of this list and you will get the result, or you can do the rest of this list, this quoted list, and you will get the result. Now, where this will be extra useful is when you have more complex structures. You don't have to quote just lists of numbers. You can do that also with all sorts of things, including variables. I mean, any identifier can be quoted and will not be evaluated, right? And that actually allows you to construct, I mean, arbitrary tree-like structures like syntax trees, right? Which you can then work with in Lisp, again, just recursively traversing whatever structure you have. We'll have more examples of that, I think you have in homework and some in the labs, maybe on Wednesday. Okay. So another thing is we talked about conditionals last time, but we only talked about if, which we sort of said that we are not going to be using because we're going to be just defaulting to cond. And we briefly had this or an and, but let me just stop on them in a bit more details for a second. So just like in your favorite programming language, when you have a series of logical expressions that you would like to evaluate with or and, typically you don't want to evaluate all of them. You only want to understand if you're, for example, evaluating or, you just want to evaluate until the first truth, and then you already know the result. Well, the result is going to be true, so you don't have to evaluate everything else, right? Now this goes against the call by value strategy, right? Where the arguments of a function are always evaluated before the function is applied to those arguments, right? So in this case, here's just a small example of computing something very inefficiently, right? And you have or and with two expressions, one of which takes quite a bit of time to compute. So what you could do here is you could look at the first argument to or the first argument to and realize that you immediately have the answer for the entire expression. So there is no need to compute the second argument, right? So again, in your favorite languages, this is exactly what happens. If you don't have to compute the second argument to or the second argument to and, you don't compute it. So what happens is these logical operators are exceptions to the rule of call by value in most languages, in Racket, including the Racket. Now, in Racket, this is achieved by using, well, essentially macros. So or and and are not really functions, they are special forms. They do not compute their arguments before applying. They compute the first one if it is true, and you can short circuit and return true, that's fine. If it's false, then you go to the second one, and then the third one, now however many arguments you have. Okay, so or and and are not functions, they are in fact special forms. This is important. Okay, do you have any question? Does it make sense? Okay, very good. So let's get to higher order functions. So simply put, higher order functions are functions that can take other functions as arguments or return them as values, right? And this is a very simple concept. So you have seen this already in lambda calculus. I mean, everything is a function, right? But in all functional languages, you can do this. And again, in all modern programming languages, you can construct lambdas, and you can pass pointers to functions, or at least or functions themselves as arguments to other functions. So why is it useful at all? Do you have any examples or ideas of why this might be useful to have higher order functions? The what? Okay, yeah, so in some situations it's convenient. So you have already seen probably map function in some other languages, okay? So in general, higher order functions is just an instrument for abstraction. So if you have a higher order function, that means that a part of your code, a part of your algorithm is sort of outsourced to the user. You tell me which function to apply it here, and I will apply it, right? So this is just a very simple tool, which allows in functional programming, it is used a lot. And what it allows you to do is to reuse the same algorithm with different varying parts. So here's an example of a very simple higher order function. It takes two arguments, f and x, and it applies f to x twice, right? So we have seen this function before. Here's another common function, which we just mentioned, map. Now, map, what it does, it takes an argument, it takes a function, and it takes a list of values. And what it does, it applies this function to every value in the list, producing a list of results. So for example, here, we apply map to a function that squares its argument and apply it to a list of numbers from 1 to 5, getting all the first 5 square numbers. Okay, so this is a very simple function. Have you seen this before? Like function map in any other language? Can you raise your hand if you have seen map function? Okay, very good. So here's another variation of the map function, which is called or map in Racket. So what it does, it has a predicate, and then it has a list of values. And then it checks if any of these values satisfy the predicate. Okay. So in this case, we ask, is any of these values odd? Okay, is any of these numbers odd? In this case, the answer is false. Okay, and of course, we also get end map, right? Now, these are all functions. These are all just normal functions. So the question is, if we have map and we have or, like on the previous slide, we had or and and, right? Why do we need or map and end map? I mean, that's convenient, but why do we need them as separate functions? Well, it turns out that Okay, yeah. It turns out that if you try to implement OR map using map and OR, which is a natural thing to try out, right? You're going to arrive at something like this, right? So you first apply the predicate to every value in the list, and then you just see if any of those values is true by using OR. But now, since you have a list and you need to apply OR to the list of values, you use apply function, right? You remember this again from last lecture. Apply takes a function, takes a list of arguments, and passes the list of arguments to the function. But OR is not a function. OR, like I mentioned before, is not a regular function, it's a special form. So it has to always be applied to all of its arguments explicitly. So if you try this, you will get a syntax error because OR is not a function. You cannot use it like that. Okay. So that is why you have this special combination. I mean, obviously you can implement OR map using OR, but that would be a slightly different implementation from this short one. So here's an example of a function that uses OR map. For example, we can implement a very naive function that checks whether a number is prime. So to check whether a number is prime, we ask, well, does any number, a number is prime if there are no divisors of this number, right, between 2 and n minus 1. So this is exactly what we do. We say, well, for every number from 2 to n, and n is not included in this range, in this case, we check whether this number, which we give this name k to this number, we check if this k divides n. If any of those k's divide n, then we will get, of course, false for the entire expression. Okay, does this make sense? Yeah. OR map is a function. It supports. So okay, so that's a valid question. Let me explain. So OR map wants to apply the function, the predicate, to a list of values, right? And see if any one of those numbers, any one of those values satisfies the predicate. But now the arguments to OR map are not expressions like odd 2, odd 4, odd 6, right? The arguments to OR map are the predicate itself, the name of the predicate in this case, right? And the list of values. So yes, the arguments to OR map, oops, it's unfortunate. The arguments to OR map have to be evaluated before OR map. That is correct. Yes, yes. So if we have some big number in there, yes, it will be evaluated. Yeah. But again, if you have some complicated evaluation that you have to do for these numbers, you put it into the predicate, right? And then you also only evaluate it for the first n numbers until you get to the number that satisfies the predicate. Okay, does it make sense? Did the question make sense? So the question again was, is OR map a special form or a function? And if it's a function, then does it mean that all of the arguments are evaluated? And the answer is yes, all of the arguments are evaluated. But because we assume that the complicated computations are put into the predicate, not in the list of values, then of course, since we do not compute inside of functions, we still get short circuiting. Okay, very good. So another important function to know is filter. So filter is a very unfortunate name, which is commonly used in functional programming languages. Now, it is unfortunate because in English, when you can filter, meaning that you only leave things that satisfy the predicate, or you can filter out, which would mean that you remove the elements that satisfy the predicate, right? So whenever you write filter, then predicate, then some list. To me personally, I mean, I'm already used to this sort of, but still sometimes I have to just run it in the interpreter to see which one it is, because the name is not convenient at all. So yeah, filter in practice typically leaves the element that satisfy the predicate. So if we say filter even, it means that please give us only even numbers. Okay, so filter even with a list gives us those numbers. And in the second example, you can see that we get the first primes up to 50. Okay, using filter. So here's an example of using filter and map together. It's again a very simple example, but hopefully illustrative. So what we have here is we have a list of pairs of student name and, well, let's say student grade or whatever. Yes. Can we define? Can we use quote? I think so. Yes. You should be able to. So you should be able to use the same notation as where we have pairs here. So the same notation should be valid. It's just that without quotation, dot is not available to you. So, I mean, lists are, you can do lists sort of without quotation, except they are interpreted as function calls, but dot is not a valid syntax without quotation, I believe, in Racket at least. Okay, let's go here. So yeah, you can do quotation, but I'm just making it explicit for clarity. So, and then what we want to do is we want to know all the students who have their grade greater than 4.0. Okay, so we can do that very easily using these functions map and filter, right? So we can write an expression like this, for example. So what happens here is we, if we start from the end of this expression with students, right? What we do is we first filter students using a custom predicate, which we introduce using a lambda expression, right? So, okay, this function takes a student, just one student as an input. Then it takes the second component of this student entry, which is the student's grade, right? And then it compares it with 4.0. And if it's more than 4.0, then the predicate is satisfied, right? And then with the result of this, we just apply map car, which means that we have just selected pairs where the second component is greater than 4.0, and now we select the first components of those pairs. So let me just show you this again. We have this list, list of 4 values, right, which is students. Then when we filter them out, we are only left with 2 pairs, right? Because filter does not change the structure, it only keeps some of the elements in the list. And then map car to every one of those values applies just extract the first component. And so we get Anna and Charles in this case. Okay, does this make sense? So it should be very clear. So which style do you think this is written in? What do you say? Is this declarative or imperative? What do you say? Declarative. So how many of you think that this is declarative? And how many of you think that this is imperative? Nobody. Okay, very good. Just a sanity check, I guess. So here's another important function to know. It's called fold L in Racket. In some other languages, it's called reduce or just fold. So this function, what it does, it essentially provides a basic looping mechanism for lists. It takes 3 arguments. The first argument is a function. I'm gonna tell you about that function in a second, but essentially this function represents the body of the loop, or one step of the iteration. The second argument, z, which I call z here, is the initial value of the state. So we have basically an iteration that has some state, and we're doing some iteration to that state, updating it with time. And then we have a list of values. So what happens is we consider the values in the list from left to right, and for each value in that list, we perform this iteration, which is given by our function f. And this function f takes as its inputs the current element from the list that we're looking at right now, and the current, which I call x, and current is the current state. So we begin with state z, then after we consider the first element in the list, which is a, right? And we apply f to a and z. Yeah, that's a typo in there. It's not fza, it's faz. So we apply f to a and z, and that is going to be the new state. So function f is just a function that updates the state. It takes the previous state. Yeah, in the comment there, yeah. So let me just go here. So this has a typo. The other thing does not. I will fix this in Moodle, but it should be FAZ, not FZA. Let me maybe write it. Yeah. Let me take a marker. Let me try to. So maybe if I don't know, how can I? Okay, maybe like this, so that everybody can see this. So we have this. We have fold L with 3 arguments: f, z. Is it visible at all? Okay, f, z, and a list. For example, a, b, c. So what happens is that this is our initial state. These are the values that we need to consider. And this is a stepping function that just performs one step of this iteration, one iteration. So what happens is we start with z, right? And then what we want to do is we want to apply just one step, considering the first element in our list. So we arrive at f, a, z. So in Racket, the element from the list is the first argument, and the state is the second argument. And now this essentially becomes our new state, okay? Which means that when we do the next iteration, so this is, let's say, z1. So we can call this z0. This is, we call this with z0. Now this is our new state. So the next state is going to be fb called with z1. Okay. Then this is our next state. So z3 is going to be f of c of z2. And since we do not have any more elements in the list, this final state is going to be the result of our function. Now, if I write this, I can write this as a sequence of equations, or I can just put it here immediately. So I know that the result is going to be f of c of, and then this, right? And this is f of b of, then there's z1, which is f of a of z. Okay. So the expression looks a little bit funny because it's somehow reversed, right? But you remember that to compute this, we first need to compute the argument of, and to compute this, we need to compute the argument, which is this. So we first compute this, then we compute this, and then we compute this. So this outermost thing happens the last. That's why C is on the outside. This is the last element that we consider. Does this make sense? When do you, yeah, like this? Okay. Okay, does this make sense? Does this make sense? So again, fold L, so fold, it's like folding. You take, the name comes from the fact that you take a list of values and you collapse it down to a single value. And this is called folding. And L here is referring to the fact that you traverse the list from left to right. There's also a function called fold R, which traverses the elements in the list from right to left. Sometimes this is more convenient to use, but we'll focus for now on fold L, since this is the most commonly used in all other languages. Again, in Python, I believe this is called reduce. This is the same as fold L. Okay, makes sense? Very good. Let's go back to the slides. Okay. Okay. So, yeah. Here is an example of using fold L to solve exactly the same problem as before, where we have a list of pairs of students. Oh, yeah. On the previous slides, we have a couple of simple examples like addition, like sum and product, right? You can implement a sum of numbers by using 0 as your starting state, then using just addition plus as your stepping function, and then provide the list of values that you want to add. Similarly for product, you can use multiplication, 1 as your starting state, right? Because if you use 0, then you will get always 0. That's not what you want probably. So, and you can do a lot and a lot of other things in this way. Now, the good thing about fold L is that the stepping function is just a binary function. So it doesn't have to be a function that accepts arbitrarily many arguments. Okay. Do you have questions about these examples? Are these clear? Okay, very good. Then let's go into this one. So again, what do we do here? So here we say, okay, we still want to go over our list of students, which you remember is just a list of pairs, a name of the student and their grade. But now we want to use fold L to solve this problem. How do we do that? Well, we know that the result of our function should be a list of names of students, right? So it is logical to use as our initial state an empty list, because we know that the result is going to be a list. So any current state is going to be a list. An empty list is a perfectly fine default value. Okay. And now what we need to provide as our first argument to fold L is a function that would do just one step of this iteration. So this function accepts as its input student, which is just one student, one pair from the list, and current, which is the current result that we're planning to return, right? So current is a list of names we already have accumulated up to some point, and student is just a pair of student name and their grade, okay? So in the body of this function, we say, if the student that we're currently looking at has a grade more than 4.0, then what we do is we update our state, right? And we don't really say that some variable changes its value. To update the state, we really just return the new state. In this case, we take the current state and we add one more name to that list, which is we add car student, which is the name extracted from the pair, and we add that to the list. And else, so if the student does not have the required grade, then we just keep the state as is. So we return the current state unchanged. Does this make sense? Okay, should not be very hard. So now let's see how it plays out. So at the beginning, so we have the students again as the 4 pairs. So the current state is empty. And then basically our function gets called several times. The first time it's called with the first student, right? Anna, with a grade 4.3. Now we look at the condition. Yes, the student passes. So they have grade more than 4.0. So we update the state. So now our state is a list, a singleton list containing the name Anna. And we now look at the second student. Okay, second student does not have the required grade. So we move on to the next student and the current state stays unchanged, right? Now we look at Charles. Again, Charles has the required grade, so we add it to the beginning of the list using cons. We look at this the last student. They do not have the required grade, so we exit the function with the result Charles Anna. Okay. Now, how would you describe this style of programming? Is it declarative or imperative? Okay, so let's vote again. How many of you think that this is declarative? So a few of you, okay. How many of you think that this is imperative? And some of you are undecided, apparently. Okay, yeah, I see. So again, I would call this program imperative because it clearly has just an iteration. I mean, yes, we're using this higher order function fold L, but really when we're implementing this function, we're relying on computing the first one, then the second one. We have a clear sort of body of the loop. You can rewrite this with different syntax, like using a for loop, and I would do exactly the same thing, right? You can even rewrite this in Python or C, having a local variable current, which you initialize to be an empty list, right? Then you update this variable using this body of the loop. So really, even though syntax can be a little bit different from your usual for loop, this is not really that much different. Okay. Can you see the resemblance of a for loop here? No? Okay. Okay. That's fine. That's fine. Okay. Yeah, we have time for this. So let's try and implement this together. So do you remember insertion sort? I know it was like ages ago. Insertion sort, anybody? No, nobody remembers what insertion sort is? Really? So yeah, so insertion sort, I mean, the name suggests that you construct a sorted sequence by inserting. You do the iteration, right? You go over all of the elements from your list or array or whatever, and you insert them into the already sorted part of the array or the list, right? So you take all of the elements in your input list or an input array, and you insert them into the result, which, well, is just a state that gets updated. Okay, does it make sense? So what we will do, let me show you this. Okay, so can you see the screen? Yes. Okay. So if you have a list and you want to implement insertion sort here, well, the first thing that you need to do is to implement the minimum basic thing that you need in insertion sort, which is insertion. Very good. So what we can do is we can define a function called insert, which takes a list, which takes a value to be inserted and a list of values that is already sorted. Okay. So how do you insert a value in a sorted list? Okay, so let's do it very, very simple. Let's just use plain recursion for now, okay? Just very boring plain recursion. Now, whenever we have a list as an input, if you don't have immediately an idea of how to use filter or map or whatever fancy function you might imagine, the first thing that you might go to is just simply considering two cases, empty list and non-empty list, okay? So this should be the default. If you see a better solution, that's great. If you don't, just do these two cases, okay? This should be your go-to thing when you're working with lists. So if the input list is empty, then what? So we return a singleton list containing X. Now, I want to briefly draw your attention that list X is not the same as quote X. And that is because if you write it like this, then this X is basically not evaluated. You are, instead of passing a value of X here, you're just passing a symbol X, okay? Because again, quotation means exactly that. You're just passing whatever is there. Now, there is a way to go around this, but again, since we're not considering macros and metaprogramming in this course, you're free to research on your own. There's a lot of interesting stuff that you can do. But if you don't have a constant value, yeah, I suggest just using list as a function. So and then if the list is not empty, then what do we do? Yeah, so the value should be inserted after all of the elements that are smaller than the element we want to insert, right? So we need to, again, check something. I could write cond inside of else, but I might just extend my cond with one more clause, right? And the question is X greater than the first element in the list, right? And if it is greater, then it has to be after this element. Okay, so then what do I do? What is the result here? So yeah, it definitely is going to be a list, right? And again, the default thing to construct a list is either to use an empty list or to use a cons, right? In this case, cons, because we know that the list is not empty. So something is going to be the first element of this list and something is going to be the tail. Now, what is going to be the first element of this list? First LST, yeah. And the tail of this list? Insert X, rest LST. Exactly, let me just bring this down here, okay? So indeed, if we cannot, if X is greater than the first element, then we keep the first element and we insert in the tail of the list. Makes sense. And finally, we have else, and this last branch means that X should be inserted in the beginning of the list because it's smaller than or equal to all of the elements in the list, right? So in this case, we just add X as the first element of our resulting list. So we can check this function. For example, we can insert, I don't know, 4 into this. Well, let me actually take a smaller sorted list, we need a sorted list, right? So if we run it like this, then we see that 4 is inserted in the correct place. Okay. I mean, looks okay. Okay, does this code make sense? Do you have any questions about this? Yes. Could you repeat the question? Yep, at least with one element. Yep. Yes. Yep, this is what will happen. So instead of inserting the value of, so this happens if you add to the end of the list, right? So when you do this quotation of X, you have a list, but with one element, but this element is not the value of X, it's the symbol X itself. It's still a list, yes. So this is what you get, right? If I try to insert 4 into a list 1, 2 with this code, then instead of 4, the symbol X is inserted. Okay. If I fix it, it works. Okay, very good. So now that we have the insertion function, how do we implement insertion sort? Well, the idea is that insertion sort takes a list of numbers, and then what it does is it adds every one of those numbers into the growing sorted list, right? So again, there is an idea of state there. You have a state, which is the result that you're building. And what is the initial state for insertion sort?
Empty list.
Yep, empty list, exactly. So empty list is the initial state. Then we also need some function and we need some list. Well, the list is obviously going to be the list that we're using here, right? At least that's a valid candidate. If we find another list, we'll use another one. Now, what about the stepping function? So a stepping function, remember, should be some function lambda, which takes an element of that list and the current state and returns a new state. So what should be the new state? Insert X current, right? So this is our list, sorted list that we're building. And then at every step, we're inserting a value from the list, from the unsorted list, into the result. Okay, does it make sense? Yeah. Oh yeah. Yeah, I forgot that I wanted to use a fold. Yeah. Yeah. Yeah, so in this case, instead of this lambda, we can also just put insert, but I'm just going to leave this like that for clarity. Okay, so this works. Let's see if it works on an actual list. So we have this X input, which is this unsorted list. Okay, let's try it on that list. And well, as you can see, the result is a sorted list. Okay, very good. So here you have an insertion sort implemented for singly linked lists. Okay. Everything clear about this example? Okay. Do you understand now how to use fold L? Okay. So now that you understand how to use fold L, it's time for me to tell you that most of the time you should not use it. Okay. Now we will of course use it in exercises, right? And again, I remind you that there is reduce function in Python, for example, and similar. I think it's also called reduce in JavaScript. And in other languages, you have similar functions. It's typically called either reduce or fold L. However, most of the time, if you need this function, well, you're doing imperative programming anyway, so just write a for loop, right? And if you're actually, what you're trying to do is actually not an imperative function, or it's a very simple one, then most likely there already exists a special case of fold L. So for example, if you need to compute a sum of numbers, well, in Racket, you could just apply plus, right? Or in other languages, there's typically a function that just sums up all the numbers, or multiplies all the numbers in the list, right? Or concatenates all the strings, like there's typically some sort of join operation, right? So while fold L is a nice example of a higher order function that is common in functional programming, you should probably not use it. Not in functional programming, not in other languages, because either you can rewrite it using a more conventional for loops, or you can use a more specialized function that does the work for you, okay? Now, that does not mean that you should not understand how to use it. It's just not particularly beautiful, as you might have seen in the previous example. Again, go here, and I forgot where I put my clicker. Okay. So yeah, so in this example, not super pretty code, right? A for loop would be much more readable, right? Would you agree? So yeah, that's the point. If you have a complicated thing, probably for loop is better for you. So anyway, we have a little bit of time, and I will tell you just a little bit about generators. So this is a feature that is common in some functional languages and in some other languages. For example, in Python, this is something that you can see a lot. And the idea is that, okay, so we have just implemented a function that finds out all student names whose grade is greater than 4. But in practice, you might be working with some data that is large. Yeah, there can be a lot of data to work with. And it is likely that you later not only use this name just to display, you probably do something else to this data. And what you typically would like to do in a real application is, instead of having the entire list of values of results, you would like to instead work with a stream of results, right? You would like to be able to get the next result on demand. Now, with call by value languages, which are most modern languages, it is not something that you can easily do. So generators, and there are also streams, there are also some other things, but today we're looking in particular at generators, is one way to achieve that. So the idea of a generator is that it is a function that is not pure, meaning that it is not deterministic. It might not be deterministic, meaning it might return different results based on whatever environment it is executed in. And for us in particular, what's important is that we want a function that will basically return us the next result in the stream, okay? So in this example, what we have is we first define this auxiliary function called loop here, just loop, which again, just iterates over the list of students, does the same logic. It just checks whether the student is has a good enough grade or not, right? And then if they do, we do the following thing. Notice the begin, yield, and loop, these 3 lines. Let me maybe highlight them here. So we're most interested in, yeah, that did not work very well. So this begin, right? This begin is again a special form that takes several expressions and just computes the first one, then the second one, then the third one, just one after another. Then yield is again a special thing that tells the generator, which we're going to construct, that this is one of the values that we return. Now, when we construct the generator, what it will do, it will stop execution of this function, right? Or rather pause the execution of this function after it yields a result. And then when we call the generator again, it will continue from the place that we left on to go into the recursive call and find the next student with a good enough grade. Okay, does this make sense? So works like magic. So yeah, so what we have here, the important thing is that if we have a student that has a good enough grade, then we do this begin block, which basically tells us return, give something to the generator, and then go to the recursive call. Okay, and then the actual generator, to construct the actual generator, we use this loop with some initial value, which in our case was predefined. We had the students already defined somewhere. Now the empty list, that is the first argument to generator, is the state of the generator, which you can optionally use, but this is a little bit complicated. We're not going to be using that. Okay, so this just gives you an example of when you can generate a stream of results one by one. Okay, so then in the interpreter, when you call this students with 4+ as a function, the first time you call it, it will return the first student, Anna. The second time, it will return Charles, and after that, it will return no more 4+ students. Okay, does it make sense? Okay, yeah. Now, in this case, we can just return it, and this will be the value that I think is going to be repeated forever. It's like the value that the generator will return when all the yields are already finished. Yeah, you can do yield as well, but then you will not have the next yield. I think that will not work with the fourth call. Yeah. Okay, that makes sense. So just to summarize, today we have seen at least 3 ways to sort of process some very small, very boring data set, right? Using filter and map, or using fold L and some imperative style programming in Racket, or using a generator to not only do this, like again, in this case, we're doing this imperatively, but we also produce results one by one. So we do not compute the entire result at once. Okay, yeah, so please spend just a couple of minutes in the end of this lecture to again let me know what was the most unclear part of this lecture. Okay.